FRQs. Okay. Can you guys see that? Yeah, you guys can see that. And it's a scanned copy, so bear with it. All right, so question. Actually find the question, sorry. Half cell, okay, so you have your half cells, you had your anode and cathode labeled. Which one did you guys decide was the anode? 10, but why? Because it what? Okay, yes, it was oxidized. And then you can also verify on your reduction potentialist that your 10 is a negative voltage or a negative E associated with it, whereas silver had a more positive one. So the higher the reduction potential, the more likely it is, reduced. And then probably hydrogen's there just as a catalyst. All right, and then those are your half reactions. And then B, write the balanced one. So you had to completely just add them together, but you did have to do a multiplier of 2 on your silver because you had to have a balanced charge balanced by electron transfer. And then subtracting, is this where our problem was? Subtracting? My voltage was different. What part of this do I need to go over? C. Okay, so this is where we hit equilibrium. So if you're at equilibrium, the cell, E cell, not E not cell, E cell is 0. So E naught cell, which is not 0 ever, unless you're subtracting the same electrodes like we just did with the Danielle's or the concentration cell, this is that cell voltage you just got there, 0.19 or 94. So as you're looking at your Nernst equation, that's kind of simplified version. This is my fave version, okay, so the log one. So if you have your E naught cell, and then each of your variables, this was 2 moles of electrons transferred because you had the multiplier involved, your log of K, well, you're solving for K because that's your equilibrium constant. So as you go through and plug your values in, E naught cell, 2 electrons, solve for K, 0.94 is your voltage you got above. And here's my little note over here. Nernst equation, at equilibrium, E is equal to 0, Q is equal to K, because we're at equilibrium at that point. So plugging in, modify, or manipulate your equation first, get K by itself. Opposite of log is 10, not E. And then plug that in, you should get something like 6 times 10 to the 31st. Yeah.
Okay, so I did like Nephi, and then I did Rock.
Okay. So if you did Nephi, did you set...
And I got 0.93.
Did you do opposite of L as E?
Yeah.
I might have to just look at your math. Because
I did it like for number 5, like on the Nernst BS too. Like it messed up all my values also.
So, honey, you said round link negative R to the L and K equals what? What did you say equal to?
So I did negative Nephi equals delta G, and then I solved for
Delta G.
I plugged that in, and then solved for the K.
Did you change your units, kilojoules and joules?
Yeah.
I might look at yours specifically, but this is the best. This is the most direct approach for sure. Okay, so oh, and that should have made sense because what do we do? Actually, no, never mind. Period. The K value is large. The delta G is negative. The E cell is positive. It's a galvanic cell. Part D, you had concentration differences occurring. So when you plug in your stuff into Q, what you should notice is that a silver ion was squared because it had its 2 coefficients in its overall reaction. So taking those, popping them into the Q place here, plugging in your concentrations. First thing you should notice is that we've changed the concentration of silver to be 0.02 versus the standard one, which was 1. So you should do your prediction first. Silver ion was a reactant. Silver ion was a reactant. If you lower the concentration of a reactant, which way should that shift equilibrium? To the left to produce more of that. If you're shifting left, are you releasing more electrons? More or less electrons? Less. The driving force is forward, right? If your electromotive force is not increasing in the forward direction, you will not have as much voltage. So the voltage should decline, which it does from 0.94 to 0.84. So that should be a double whammy, like, hey, I predicted we should go lower because it should shift left. I plugged in the values. I got a lower value. I've done it correct. Okay, you should have those little back safety nets, right? Okay, number 8, 1983. Scooching through that one. Oh, I remember this one. Okay, so you had your titanium. should have your, so Brownstone acid, you guys just had to do half reactions first. Oh, sorry, no, I'm on the wrong question. The other one had titanium. Okay, so you had your overall reaction, told you it was an acid, so you had to do your half balancing in acid, titanium to TiO2 plus, and then this is a weak acid, so you do not ionize it at the end, just FYI. You are adding H's on left and right. This one had 1 electron converted or lost versus 2 electrons gained, so you had to then multiply the top half reaction by 2 to get your overall charge balance and mass balance. Did everybody get this far? Where was the struggle at here? Just some odd stuff? Oh, yeah, don't forget your oxidation reduction has to be balanced. So I'm going to leave that like that for a second. And C, the question was, oops, I keep looking at the wrong question. Concentration species is 0.1 molar compared to the cell voltage that was observed with the standard cell potential. Oh, was the problem that you guys didn't have this on your reference table? Reduction half? Was this one? Second, you looked up. I have like 4 more, and they're very long. They're very, very complete. Yes, I might need a copy of the other reference tables for you guys. So first of all, I'm gonna scroll back up here. So it's basically saying we're decreasing the concentrations of ions from the 1 molar standard to the 0.1 molar new concentration. So 0.1 molar, 0.1 molar, 0.1 molar, 0.1 molar, 0.1 molar. Who decreased more, reactants or products? We basically have how many moles of ions over here? I mean, how many moles of aqueous ions or aqueous acids? 3. 1, 2, 3. Over here we have 6 moles of ions or aqueous products. If you were to decrease those equally to 1.0 to 0.10, who would have a more severe decrease? Products. So if you're decreasing the products more than you're decreasing the reactants, still what should occur? Shift. You're decreasing this one. You're decreasing the reactants less than you're decreasing the products. If you decrease the products more, it should continue to shift right to try to elevate the product concentration once again. So if you're shifting right, it should increase the overall E cell because your voltage should increase. So basically, yeah, so here's our overall. I just did the titaniums. I ignored the aqueous acids. This decrease causes this equilibrium. It's going to shift right to reestablish equilibrium just because of the nature of the number of moles of ions. Does that help with that one? There's a bit of weirdo. All right, anything else on question on 1983? This one was interesting because you had to go through the identification of things that related, so variables that related. Who said delta G? Awesome. I thought that was a pretty obvious one because it just dealt with that. K and or pH, actually, because this one had some H pluses within the overall equation. So we can talk about that more in depth too. Okay, we're going to do electrolytic now. Okay, get ready for me. Oh, I have printed. We're going to have this chart we'll use, but I did print it in your notes, but I thought this was bigger. So Jacob will make sure everybody gets one. Thank you. And then nothing, shut down your computer, close it so we don't spill anything on it. And let's go. Alright, so you should probably actually, by default, already know a lot about electrolytic because it's everything opposite of galvanic. Work with me here, people. We're going to go through some stoichiometry in a second. Yeah, stoich is coming back, okay? So in the galvanic cell, we took what energy and converted it to what energy? Chemical to electrical. That was galvanic. The chemistry behind it was driving the electrons to be produced. We captured them. We moved on. So in this one, we're taking electrical energy and we're changing it to chemical energy to push electrons in a way that they normally wouldn't be pushed. And so this has to be a coupled reaction because coupled reactions are going to take that galvanic cell and it's going to use it with an electrolytic cell. And the energy that's given off from the galvanic cell is going to drive the electrolytic non-spontaneous reaction to occur. Because non-spontaneous reactions, they don't occur, right? So you need to get them to their appropriate activation energy, or give them enough energy to get started, spark them, I guess you could say, to get started. And that's not just going to come from anything. Generally, it's going to be coming from another galvanic cell. And we're going to diagram how these look a little different here. So we talked about that. Pumps electrons to the cathode, because that's how we're going to build up charge to actually force the acceptance of that, so that they will then do their chemical process of whatever their oxidation reduction is that they have to do. And so I have a definition of coupled reaction, but it's at the very bottom. But it's basically taking a spontaneous reaction, pairing it with a non-spontaneous reaction, allowing that delta G, that energy that's given off. Remember, delta G is energy to do work. It's going to do work, and it's going to force the electrons on the other side to move. So here's your basic setup. This one is our galvanic one. This one is our electrolytic one. This is not how we're going to draw though. This one has a salt bridge. We're actually going to draw them with a porous barrier. I have it in 2 slides. So that's going to give you a distinct diagram difference. Galvanic has 2 separate compartments. Salt bridge in the middle. What's the purpose of the salt bridge for galvanic? Say again? No! Not full of electrons! I swear, you guys cannot say that. I'm only saying that loud and proud because people put that on the exam. So, flow of electrons goes to the outside. What happens here? Okay, we're going to say ion charge balance, something like that, so that we have the electrolytes flowing back and forth to help with charge buildup, because if you get charge buildup, the electrons just won't flow. Okay, so electrons are only going to flow through external wire. And that's what the 2014 exam, they actually had people draw what was in the salt bridge. Half the nation put electrons. Okay? Alright, so this is why I can't grade in front of you. I get emotional. Okay, so whenever you have your battery, it's going to be that the battery will still have an anode and cathode. It'll be paired with the opposite anode and cathode of the electrolytic cell. Alright, so if you're thinking about terminology switching, don't do it. Cathode will always have the process that is reduction, and it will always have the process that's oxidation. It doesn't matter what you're dealing with. They are describing the process. So, for example, if I have an outside battery pushing electrons someplace, that place it's pushing it is towards the cathode, because the cathode will receive electrons. The other side of the battery will be accepting electrons from another location. That will be the anodes that's giving it up. The process is what describes the terminology here. Real-world applications, electrolysis of water. That's going to take water, split it into hydrogen and oxygen. Does that happen on the regular? Is your water just in your bottle just like poofing into gases? No, it'd be crazy. Like, catch it now, hurry before it decomposes. No. So that's not spontaneous. It's not happening in everyday life. So what we can do is we can force our electrons to move in a specific way, force electrolysis. Electroplating, who has jewelry on? Okay, most of your stuff has probably been electroplated through chemistry. So it's got a layer of nickel or titanium or some other metal that's not what the core is made of. Or by isolating. So in the real world, stuff's not pure, right? We have to make it pure by isolating some sort of contaminants or impurities from it. So like in an iron mine or a copper mine or something like that, they'll get these big chunks of rock, and inside of it will have metals. And so we extract the metals through the process of refining, and that's going to allow for us to isolate pure metals from impurities. So there's a lot of real-life applications here. Along with that, we also can now find the amount, okay, so the amount probably is going to be in grams, of a reactant that we can turn from its aqueous state to solid or vice versa, which is now where we're going to get that stoichiometry coming back. But it is going to be based on the voltage and the number of electrons transferred. So that's where we're going to have volts, joules, coulombs, moles of electrons, Faraday's constant, stoichiometry, molar mass, okay, or mole ratios, molar mass. We're going to throw all that together here at the end. So here's my car. It's not my car. So chrome-plated wheels. They do it with electroplating. Gold, anything that's gold-plated, rolled gold, gold electroplating, same as plated gold. So there's some different markings you can see, like at the jewelry store, if you're in that field for some reason, and you need to see what's been plated. It's usually going to be through electrolysis. Okay, let's kind of big picture. Narrowing down. Let me come back. Yeah. All right, this is our sketch. Sketch for me first. I did it all by myself. Give yourself a sketch of this, because we're going to talk about the anatomy of electrolytic versus galvanic. It's one big old beaker, guys. One big beaker with some sort of like porous barrier, like a filter paper or something like that in between. There's not a true salt bridge in this case.
CC is direct charge.
Direct current. Yeah. And we're still going to have an electrode called the anode, and one of them called the cathode. But notice there's no compartments anymore. There's no like anode compartment and cathode compartment because it's all in one big beaker, one big petri dish, or one big tub vat of sorts. So we're still going to call one the anode and one the cathode, but it's all going to be based on the process occurring there. So what are some features you see? I heard Jack tell me one.
Barrier. Oh yeah.
The what? Direct current. What do you guys think this is? This is a like a 9-volt battery. Oops, I can't write on the board when I don't have it on. That's like a 9-volt battery or some other battery that is galvanic. Okay, so I'm just gonna put 9-volt up there. We'll label the charges in a second. You still see an external wire because we still need an external wire where electrons will flow. You see our metals, our solid metals are metal objects that would be considered anode and cathode. And I put molten salt or water down here. That's the only two cases we'll ever have. Molten salt, where you have a liquid salt, basically it's melted, or aqueous solutions. That'll be it for our examples. So I'm scooch back here. Let's look at this example here. So first of all, I told you a couple of reactions. So if it says voltage source, that's the galvanic cell that's giving off the free energy to do the work. And so you can still see plating. This is like a ring right here. So they've taken this ring, that's a metal, they've clipped it to this side, and they're delivering electrons here. So when you're delivering electrons to this side, what is happening? Oxidation or reduction? Reduction, okay? So this one is called the cathode of the, and if you want to diagram this on yours, I'm giving you a nicer example and I'm going to work from here, but this is called the cathode because it's gaining electrons. Well, as this silver ion gains one electron, it's going to form silver. Where do you think that silver solid is going to go? On the ring, right? We're making a sheath of silver that's plated on that ring there. So that's how it's called electroplating. But that silver ion is floating all around in solution all together. Floating. So that silver ion could be what the actual solution is made of, or it could be the silver ion that's popping off of the anode. So the anode is the opposite process. We have the oxidation occurring. So you can see that this has an arrow pulling the silver ion off. Well, why would it do that? Why is that silver ion coming off? Because it's losing an electron. Where's the electron going? Up the wire to be given to the one side in particular of this battery. So the electron's being pulled off. It can't stay there. It's no longer solid. It pops off into solution. It dissolves into solution. So we have now the other half reaction, oxidation occurring, because this is called the anode. It's still made of silver, but we still have the process of the electrons moving. So now you can think about it from the galvanic cell's perspective. This is the electrolytic cell down here. If this side is the anode and it's giving off electrons, what does this side have to be of the galvanic cell? It cannot be the anode because both of these can't lose electrons, right? It has to be the cathode. Okay. The reason why this is the galvanic one up here is because if this is the anode, it has to be delivering electrons to an opposite counterpart. It doesn't have to be within the same solution. It's just an opposite counterpart. So it's going to be giving it to the cathode to be reduced. Well, normally our galvanic cell would give its own anode electrons to its own cathode, but when you couple it, it doesn't have to. So this is still the anode of the galvanic cell delivering those electrons to the cathode of the electrolytic cell. Why is there already inherently charge balance here? For every silver that turns to silver ion,
Silver ion turns to silver.
right, one of the silver ions turns into silver solid. So it's inherently balancing its own charge in that entire solution because there's both reactions happening at the same time. No need for a salt bridge itself. sometimes you have ions that, sometimes you'll have particulates that form, and it helps compartmentalize them. And also sometimes you'll have molten salts, and molten salts from crystals, so it helps to segregate them somehow. So we're going to talk about the molten salts in a second, okay? So this is a circuit between two cells, galvanic and electrolytic. Who's driving who? So the galvanic is driving this to occur. If you took the galvanic off of this, nothing would happen. The galvanic is pulling the electrons from the silver to the cathode. The galvanic wants to give up its electrons, so it gives them up, and it forces the reduction to occur over here. And this causes charge balance within. So that, say again?
What's the point if you're using a battery to make energy?
Because silver won't plate itself.
Okay.
Silver, so if I want something to happen, I set up a situation where ions will flow. And so this might be a really impure form of silver, maybe like an ore, and I can have a rock with a little bit of silver in it. I can hook that rock up to an electrode. I can pull the silver out without even touching it, and it'll plate on something else. Magic. Okay, I think that's probably it on this one. Okay, so this was just a fact, because we're going to talk about this stoichiometry in a second. The amount of product that's plated, so you can see my little diagram down here. Guys, focus. It's distracting to me. I'm sure to everyone else. So this right here is your little beard. That's your plating occurring. The mass that's plated there is directly related to the number of electrons that flow. So we're going to get to that now, okay? But before that, let's chat about what in the world we would apply this to. This is on your chart, I think. Is this? Maybe not quite yet. Okay, like I said, there's only two situations we'll ever apply this: molten salts. Write this down for yourself someplace, maybe on the back of that. So molten salts or aqueous solutions. And if we have one case or the other, we prioritize our rules differently. I'll see what the rules are in a second. So if we have a molten salt, give me an example of a molten salt. Do not say sodium chloride. Get creative. Whenever you're ready. Anything ionic. Okay, potassium. Don't say chloride. Iodide. Fantastic, guys. Something other than sodium chloride is on the board already. So if I have a molten salt, there's nothing there but that K plus and that I minus. Nothing else. So if you're trying to figure out between these two, which process or which ion is going to be of interest to the cathode and which is going to be of interest to the anode, you just have to think about what can they do. What can potassium do? What can potassium ion do? Sorry. It can only do one thing. Can it gain or can it lose electrons? It can only gain electrons because it doesn't have any more electrons to lose. If not, you're going to inner core electrons, and we don't touch those. We only touch valence electrons. So you can make it gain one electron to form what? Potassium, which in itself is very reactive with water. So we wouldn't want water in here. It's explosive with water. So that has to be gaining electrons. So that has to occur at the cathode rig reduction. And then iodine, second example, iodine I1 minus. There's only one thing it can do. What can it do? Lose. In this case, how many? Okay, so you want me to write I in one electron? Doesn't that just look ugly? I2.
And then
two I ions. Okay. So iodine cannot gain electrons. It can only lose electrons. So it doesn't have a choice. It must be oxidized. So it must occur at the anode. Right. So this example here helps you see the cat ions are at the cathode, and the anions, I mean the negatively charged ones, are at the anode. That is the best way to think about it for ionics or molten salts, because there's really nothing else that you have to work with, so those are very, very easy. It helps you identify which process is going to be at which electrode. The only other thing that you might have to do is if you don't have a solid, which you don't, you will have to use platinum as your electrode solid, because ions, K plus, and ion, I minus, they're not solids, and that's the only thing initially present in the reaction, so that's why you need platinum or graphite or something like that to facilitate your process. Thumbs up, can I move on? I'm feeding you information, we're going to practice in a second. So the other side, this is just an example of that battery, okay? Molten salts, many times they use it with elemental metals like alkali or alkaline earth metals because that's how we can get them to their pure form. So this is kind of an example of that. If you have a gas though, you think about how to exhaust, create an exhaust for that, not just in a closed system. If not, it will explode. So that's that. Okay, so this is the second one, which is I think the box is underneath. It talks about aqueous solutions. So this is how you prioritize when you're looking at aqueous solutions. How do you figure out who is at the anode and who's at the cathode? Because now you have more than two choices. The first example, you got two choices, you have 50-50 chance of getting it right. So this one, you have to consider a couple more ideas. At the anode, there are only two options. If you have a halogen or a halide ion, they are like more than willing to give up electrons whenever you apply a force. By themselves, they won't do it because they want those electrons. They're octet, right? They definitely want the electrons, but they're the only ones with extra electrons to give up. So the halides, any of those like we kind of just did, iodine, chloride, fluorine, bromine, things like that, they are going to be able to give up electrons and either have two electrons flow off to make something diatomic, or you can do a half one, but that's always a little bit weird, so I tend to stick with the two. So that's your first priority. If you do not have a halide present, you have an aqueous solution, you have to let water do the job. So water has to allow for oxidation to occur, but water can do both oxidation and reduction. That's why it's like our second tier. If you have a halide, it's priority. If you have water, if you don't have a halide and you have water, which we will because it's aqueous, you have to let it do its job. And then tell me how this worked out. Now I'm telling you the straight up balance or half reaction. How could you figure this out yourself? Water has to be oxidized. Which component is the one that's oxidized, H or O? O, because it can go from what oxidation state? -2 to 0. Okay, but we don't just write O, we write O2 because it's diatomic. Okay, so that's our free element state. We can see the oxidation occurring. Now you balance it by adding, assuming an acid, H pluses, right? So, oh, actually, no. So there's two oxygens here. What do you have to do over here? Put a 2. So I'm going to just put a 2. Instead of adding a separate water, I'm just going to put a coefficient of 2. So then how many H pluses are over here? 4. So there's our 4 H pluses balancing an acid. And then charge balance. Net charge over here. 0. Net charge over here. 4 plus, so you add your 4 electrons. So you definitely can do your own balancing of that. I just want to give the whole thing to you first. So this is all occurring at the anode because oxidation is present. Oh, and so this is if any other ion other than halogens are present. Okay, so now priorities for the cathode. If your substance is acidic and it's electrolyte, it's like a strong acid or something, you have H plus is present, they will readily accept those electrons back to form hydrogen gas. That's a pretty prevalent reaction if you have an H plus present, or if it ever says in acid. If you don't have an acid present, you have to choose the next thing, which would be usually a transition metal, which would likely accept electrons back with the free energy that this galvanic cell is giving it to force it to do something it normally wouldn't do. So I say transition metals because like tin will gain 2 electrons back to form tin solid and so forth. This is pretty inert compared to some of the alkali metals. Like I just said, what happens when you put potassium in water? It explodes. Have you guys ever seen? I have some potassium back. I'll do this tomorrow for you. I have potassium, sodium. That's all I have. I don't get to use it frequently, so I'll do this tomorrow. But yes, alkali metals, they react really, really easily. They will react with water and make fire. So we try to stick with transition metals to be our secondary source of a cathode. Tertiary source of a cathode, if you don't have an acid, if you don't have a transition metal, you have to choose water. Water is the thing that will react with your cathode. So if you do the reduction of water, it takes a little bit more effort. Why can't this be balanced in acid this way? This is my note to self. I'm not allowing you to choose this if an acid is present. Because what do you have to reduce if an acid is present? The acid, right? So this would be the case if it didn't say an acid, because if it's an acid, screw water, you're using the acid. if you don't have acid and you don't have transition metal, you have to reduce water, but it's going to be assumed to be in base, because if it were an acid, you would have done the first step, the first priority. So that's why we bounced this in base as a reduction. Okay, those are your rules for setting up an electrolytic cell. If you have if you have a molten salt, what goes with the cathode? Molten salt, cathode. Cathode, cation. If you have a molten salt, what goes with the anode? Anion. If I have copper 2 chloride, aqueous. Copper 2 chloride, aqueous. Who goes with the anode? Look at your nose. Why are you laying on your knee? Anode. The chloride, the halogen. Copper can't be reduced or oxidized anymore. It's already copper 2. I've never heard of copper 3, right? It will not oxidize anymore. So copper 2 chloride aqueous, who will occur at the cathode? You say what? You said copper, but why? That's right. Right, but you went through your priorities in your head. You didn't have an acid because I didn't say acidic solution. It happened to fall under the category of a transition metal. But if I had said sodium chloride aqueous, who would be at the cathode? Say again? Water. Sodium's not an acid. It's not a reducible metal. It'll cause flame and fire. We'll lose our battery. It has to be the water. All right, so let's go with that process in a second. We're going to set up our own cells in a second. So let's go ahead and do our circuitry. So if you guys remember a little bit of this from last week, amps, coulombs per second, it's amount of flow. It's like a rate of flow of electrons. This is just a fun fact. I thought it was cool. 1 amp is like 6 times 10 to the 18th electrons per second. That's a very large number. Wow. Okay, thank you. And then this is the only thing that really I think is probably important to write down. If you're trying to consider how to change your amount of electron flow to force a reaction to occur, you need more surface area. And so it's not about how much, like the mass per se, it's about how much surface contact there's present for that layer of oxidation to occur, that layer of reduction to occur. And this probably makes sense, but larger batteries, they have more space to work with, so you can change up their concentrations, so they can hence usually create more current. So larger batteries can have either higher concentrations or increased surface area within. That's probably about all they have for their as an advantage, so they can create more current. All right, do me a favor, get up and stand and talk to somebody. So I need you guys alert for a little bit longer. Come grab another donut hole. Savannah, I'm sure she knows anything about this. Quick break. Quick break. Mm-hmm. Wow. All right, if you want to go ahead and write down anything else on the board, do that. We can get another second for break, because I know I've been waiting for a while. You saw that out. If you want to get your laptop up now, that's good. Do that for me. I'm trying to look for you. I only have 10 more minutes. Oh, good. I have no time. They cut our, because with intervention, I lose time. Intervention.
That's so weird.
Intervention from 10:15 to 10:50. All right, on delay. No, but I need 10 more minutes, and I want you guys to practice in class. So.
Okay.
Yeah. Rapido. All right, Lucas, we'll just get caught up here. You just help him out sooner. All right, so on the reference table on the back where it has electrochemistry, it says I. I means current. I means current. If you do not know that I means current, I think it even has like a variable list of definitions. Write that down for yourself. So if I means current, that means I is actually the ratio of charge per second. So I, amps, is coulombs per second. So if I have something that's like 2 amps, oops, I just put molar, because you should say molar. 2 amps, that means that's 2 what? Coulombs per second is flowing. So you can easily convert amperes to coulombs per second now because you know the relationship between current and coulombs per second. So you know that. You already know Faraday's constant. 96,500s are kind of abbreviated like that. Coulombs per, coulombs not coulombs per second. Coulombs per what? Anybody? Moles of electrons, right? So it's talking about the charge that a mole of electron carries, and then we already know the other ratios that we ever use will be more likely to be mole ratios. So let's write down our givens for question 1. I'm trying to hit like 3 of these with you guys, and I think we're good. Write down your givens for question 1. What mass, so question mark, grams of copper, so grams of copper is our overall question, is plated out, so think about, like, the general set plated out, when 10 amps is applied to a copper 2 sulfate solution. I'm going to put AQ back there to remind you solution means aqueous solution for 30 minutes. That's it. Which of those is my starting point? Okay, so good point. I just finished this with honors Chem. The fact that is non-conversion factor based is the given that you start with. Amps, it looks like a given. That's more of a conversion factor. What does that actually mean? Coulombs per second. So if you feel like writing amps, write amps. But if you feel like writing coulombs per second, I think it's very clear now. You have to start with your given of 30 minutes, convert that to seconds. Okay, so I'll stick with that, but there's one more thing I want us to do, and I think you'll see it when we get there. So go ahead and convert 30 minutes to seconds. 1 minute, 60 seconds. Okay, what conversion factor would you use next? Okay, so the what over what? So 10 coulombs per second. Okay. So far, so good. What would you do next? Say again? Sorry, I thought I heard you guys say that, but I wasn't sure. So Faraday constant, what goes on top? 1 mole of electron carries 96,485 or 96,500. I think I have to look and see what I used because that might affect my answer. So you guys know enough about how to put a puzzle together. Even if you don't know what you're talking about, you can put a puzzle together. But here's where you have to know what you're talking about. Mole of electron. What is that regarding? What is it talking about? The BCE. Okay, I hear that. What's the BCE? No, we can't use mole ratios yet because we don't even have the electron transfer. So we need to write out, just like you do with your electrolysis. Oh, sorry, yeah, with electrolysis, because you can see, first of all, I'm powering this thing. I'm powering it with a battery, right? That automatically tells you it's electrolysis, an electrolytic cell. You need to write out your copper 2 sulfate. Ready? Write out your copper 2 sulfate. Think about it being aqueous. Assign something to be the anode. Assign something to be the cathode. So what are my options here? I have copper ion, I have sulfate, and I have water. What has to be my anode? Okay, I already know who's going to be the cathode. I hear that. Leave that out. So think about your anode. Go back to your notes. You're not looking at the molten salt. You're looking at the aqueous. First priority is, if I had it, it would be what? halide, I don't have a halide, okay? Move on.
Oxidation ratio.
Has to be the oxidation of water. Okay, so water's oxidation is, if you don't have to memorize, okay? Water makes oxygen, double your water to create your oxygens equal, and then add whatever here. 4 H pluses and 4 electrons. Okay, that is actually your anode. Now there's probably platinum sticking in there, right? Because that's not going to happen by itself. It needs a surface to contact. And then, so that's your anode, because that was by default. You had to get to water. We would definitely use your cathode. Copper ion, gaining 2 electrons, Cl copper. Can you see this blue okay? Yeah. Okay. And then, yeah, so we have oxidation reduction. Go ahead and tell me how to proceed. Multiply the bottom by 2, because I need 4 electrons total exchanged. So then I have 2 waters plus 2 coppers, copper ions, sorry, yields oxygen gas plus 4 H pluses plus 2 copper solids. And then take a minute to reflect here. If you see this reaction happening, what are you going to see? What would you observe? So you'd see that kind of nice copper color being plated on whatever the other electrode was, and you'd see bubbles, because you see the oxygen. You can light a match, you can even test for the oxygen. What would happen to a match if you had oxygen and presence of a match? Okay, so not that big, not like a nuclear explosion, but like a little extra fire there, okay? All right, so now thinking about that, what's next here? Moles of electrons. I have to get rid of them. So what do you want to convert to next? Copper what?
2.
Let's just go straight to moles of copper, right? We have the relationships up there. So just narrowing down. So that's the full reaction, but just narrow down to copper. What happened here? For every, well, either way will work out. I'll do it according to this, and then I'll go back. Either you can do 2 moles of copper created for every 4 moles of electrons transferred, or back to your half reaction, for every 1 mole of copper created, 2 moles of electrons transferred. Isn't it the same ratio?
Yeah.
4 over 2 or 2 over 1, it doesn't matter. I'll stick with just the copper half reaction. So 1 mole of copper created, it had to be involved with 2 moles of electrons being transferred. So that gets me out of moles of electrons. Now I'm in moles of copper. Last step, molar mass. 1 mole of copper, 1 mole of copper, 63.55?
Yes.
63.55 grams of copper. That's your last step. Go ahead and calculate for me.
$30.
Anybody?
Seconds.
5.93 grams of copper. There we go. So we would collect, if we let this battery run for 30 minutes at 10 amps, we would collect about 6 grams of copper. So you can imagine if you had to scale this up, you could, but just by adjusting a couple of the variables, assuming that you still had enough of the copper ion in solution. So, all right, let's do. You guys do number 3, and this is actually in your notes. Open up your packet to. I might have to look at somebody's packet. I might have to look at someone's packet. Go to number 3. It's on page 7. I think I will totally liable. Extra question. Curveball, back up here. Curveball. Did not print this question for you. Okay. How many minutes will be required? So what's our question?
5 minutes.
Time, okay. Will be required for a 1.5 amp, which I'm not writing as amps, I'm writing as ohms per second, to electroplate 1.97 grams of AUs. And assume that 1 electron is transferred per 1 mole of gold. What does that mean gold's charge will be? +1. Because that's not a very common one you see, right? You don't just know gold's charge. And it's falls right under silver, so that behaves very similar to silver. That's why it has a 1. All right, go ahead. Figure out where to start.
Oh my. Okay, 1.97 times 1 mole over 96.9. I think it's 196.9. 197. 96.9. You see how good I am at guessing, or not guessing, but I said I guessed 196.9. I didn't realize it until I actually said that, but I still guessed 196.9. Don't touch my arm like that.
What's up, Alan?
Assume 189. Higher electron transfer.
It's
Times 9645 coulombs per mole electron times seconds of 1.5 coulomb times minutes over 60 seconds. By 197, it's up there, times 96485, divided by 1.5, divided by 60, 10.7, Whoa, so cool. You have an extra water bottle by chance? No. You have an extra water bottle by chance? Like the water bottle?
Alright, if you get done with this one, go ahead and move to the next one. Once you get done with this one, move on to the next one. Sean and Jacob, move on. Yeah.
Yes, and you multiply that by 1.5.
Oh, I didn't have 645. You do, yeah, over 1.5, and then that over 60, or 60. And that equals, I got 10.7.
Say again. 10.72 minutes.
Oh yeah, I got exactly twice that, so I'm on the right.
We're on it, doggone it.
Hold on. Say again. What'd you do with 2?
Well, I got 21.44. So.
Oh, where's your 2? Are you writing your workout?
Yeah.
I believe you. Yeah, guys, if you don't write your workout, no credit. Because I know that you are smart enough to do your logic in your head. Like, you could figure out how many pounds of flour you need to make, 100 bagels if you're doing it. I know that. But I need to be able to give you some feedback. I can give you feedback unless I see your work. Moving on, I'm videoing. If you need to see my work, come back to it. All right. So I have like 5 more minutes with you. I'm gonna choose the hardest one I can give you.
Oh, yes.
Either number 4, number 7 it is. Start writing your given. I don't know if I put this one on yours.
So, 2.60 liters. You have to actually. Wouldn't you find moles using alcohol? Yeah, you do.
You can't lie.
So PV over T for them. So that means that
That's
738 or 760. 2.62 over equals 738 by 60 times 2.62 over 299.2.
Has anybody written a half reaction yet that would make oxygen? Start with that. What would be a good half reaction to make oxygen? Water at the anode or cathode?
Water is going to reduce.
It doesn't say anything about a cathode here, right? But it does. It gives you indication your platinum's at the anode. So does that make sense that water is the thing? No. Platinum's not doing anything. Platinum's an inert solid. It's there for contact. Water will connect or contact platinum to force the electrons to be lost. So you're producing oxygen. Oxygen being given to zero, you know, we only ever have negative oxidation states for oxygen, so it can't be reduced, right? There's no such thing as going below that. Going below whatever its oxidation state would be. So if anything, water is at the at the anode with the whole platinum deal, because that's the solid contact it has. We've balanced this about 3 times today. Okay, so we have our half reaction. That's only relevant because we need to know how many moles of oxygen is related to the electrons flowing. All right, so what did you guys start with? Start with what? EVs and RT, right? What are you solving for here? Moles. Okay, so N equals PV over RT. What's your pressure?
738 over 760.
1738. Okay, so millim. Sorry. And that's going to give me the atmospheres. And then
Divided by
760 millimeters of mercury.
oh no, times 2.62.
0.262 liters.
And then over 299.2.
What?
299.2.
What's my R constant?
Oh, 0.0.
0.0821 atmosphere liters per mole. Okay, where does my atmospheres cancel out?
Well, at the top, because it's 738 over
With this, because this is 1 atmosphere over 760, which is my conversion in here and there.
and then 299.2 because it was 26.2. So that's just 273.
So I'm doing all my math up here on the board in step, so work with that. When you calculate how many moles do you get?
0.104.
0.10375. I'm not rounding yet, so I'm extending that. My bad. Okay, what do I do with my moles?
Now you're going to
Okay, with the electrons. 1 mole of oxygen delivers how many electrons? 4, according to my half reaction, which you have to write down for me. There is no, oh yeah, I just remember it. Write that crap down, because I will not know that you know what you're talking about. So moles cancel, moles of electrons. I'm converting to time, so how do I get this mole of electron out?
We're going to do the 96.
So Faraday's constant, 96, 500, or 485 coulombs is related to 1, not second, mole of electron. I keep writing seconds for some reason.
And then times, I think we said, what was it? I don't remember what the
Put a 2.13 coulombs per second, and I could keep it at seconds. It doesn't ask for a specific amount of time. I went to hours because it was just if it's a ridiculously large number, a ridiculously small number, convert it to a number that makes more sense. So that's like 1.8775 times 10 to the 4th second. Like, I have no perspective. Like, I can't figure out what that number really means. When you convert,
Attention, this is just a reminder to teachers and students that the intervention schedule begins this week. When the bell rings at 10:10, students will go to their first period class. Thank you.
all right, homework. Let me tell you what's up here. I'll do some more examples of this later, but we didn't get to the part where I wanted to get, so here's what I'm adjusting. I will update the website as soon as I can. Finish the problems that you started, which we did like 1, 2, 3, 4, 5. You guys do finish up 5, 6, 7, and I want you to tackle some of the FRQs that you can. Because we have a lab tomorrow with electrolytic cells, but I was going to give you guys some time to plan. So I'd like to have that time to plan with you tomorrow, but not something you can at home. Probably my guidance tomorrow to be able to finish up the problem set, then knock out some of the same sum. Because you see those little like tips on what like 2, your little thing right there.
finish the water.
I know, it's
The water.
No. In the water, Chris.
No, I need to clear out of water. I'm not. I didn't buy one at lunch. I just feel weird. I don't have cash. Yeah, but the card never works for me. I might try it.
You pay for them, right? What? You pay for them.
Yeah, give me my card.
It's on your
Yeah.
You have to make cards.
for kids' tickets. And there were certain things we could say. Happy birthday was one of the things we could say. We could say happy birthday. No, we can't. We can't.
Yeah, I know.
She doesn't share them. Bye, and we'll have some time tomorrow. We'll have intervention tomorrow, Allie. We'll have intervention tomorrow, so that's why I'm thinking you guys want to